Hello viewers, in today's video we will discuss about differentiability of a function at a particular point. What is differentiability? Actually, differentiability means the possibility of drawing a unique tangent at a point of a curve. For a function f(x), a function f(x) is said to be differentiable at a point x equal to a if limit h tends to 0 f of a plus h minus f of a by h exists, that is exists and finite. That is limit h tends to 0 minus f of a plus h minus f of a by h is equal to limit h tends to 0 plus f of a plus h minus f of a by h. This is called left hand derivative, this is called right hand derivative. We can denote them by LHD and RHD. In many books they denote it by LF-A and this by RF-A. So, what is limit h tends to 0 f of a plus h minus f of a by h? Actually, this value denotes the value of dy by dx of a function y equal to f(x) at a point x equal to a. That is, this is note the value of dy by dx at x equal to a. We can write this as value of dy by dx at x equal to a, or the value of f dash a denotes the slope of a tangent at x equal to a. Now, if limit does not exist, that is the tangent having different slopes at different direction, when it is x tends to a plus, when I approach from the right side, then the slope will be different than the if we approach from the left side. Now, what is differentiability? Actually, differentiability can be defined geometrically as the possibility of drawing a unique tangent with finite slope at any point of a curve. It is not possible if you draw more than one tangent at a particular point. It is not possible geometrically. So, what is differentiability? It is the possibility of drawing a unique tangent at a point x equal to a of any curve with finite slope. If you are having infinite slope, then it is not possible. Okay? That is why we said a function f of x is said to be differentiable at a point x equal to a if limit h tends to 0 f of a plus h minus f of a by h exists and it is finite. Now, when limit exists, we say the left hand limit and right hand limit are equal. So, we have written limit h tends to 0 minus f of a plus h minus f of a by h is equal to limit h tends to 0 plus f of f plus h minus f of a by h. This is called left hand derivative or L f dash a at the point x equal to a, and this is called R f dash a. Acha. In other words, we can say a function f of x is said to be differentiable at a point x equal to a if limit h tends to 0. Now, we will write h tends to 0, f of a minus h minus f of a by h is equal to limit h tends to 0, f of a plus h minus f of a by h. These are the same things. This is your left hand derivative, this is your right hand derivative. Or in many books they write limit x tends to a, f of x minus f of a by x minus a exists. Or you can say x tends to a minus is equal to limit x tends to a plus f of x minus f of a by x minus a. There are three different conditions are there. If these are equal, then we can say function is differentiable at that point, that is a unique tangent can be drawn at that point with a finite slope. Now, we will try to find the geometrical meaning of this using some diagrams. What is dy by dx? It is the slope of the tangent of a curve at a given point, and we know that. Now, what is slope? Slope means tan theta. Tan theta. Now, let this be the xy coordinates. This is your fx, any curve. Let x comma y be any given point on this curve. This point is capital P. Also let q x plus del x and y plus del y be a point on this curve. If P and Q are very close to one another, that is if point P and point Q are very close, then del x is tends to 0. Del x is tends to 0 when they are very close, that is PQ curve, PQ arc will tend to become PQ line. This is curve, this is PQ chord. Now, this is your del x and this is del y. If I draw a tangent at the point P, it will be, this is your tangent at the point P. When point P and point Q are very close, that is del x tends to 0, your PQ arc will tends to PQ chord. So, your the tangent at the point P will coincide with the PQ. So, dy by dx of the tangent will be is equal to tan theta. This is your theta, this is your theta, this is tan theta is equal to del y by del x, but del x is very small, so we must write limit del x tends to 0. This is your dy by dx of the tangent at x comma y is equal to limit del x tends to 0 del y by del x. Now, what is del y by del x? If you can manipulate, this is limit del x tends to 0. This is y plus del y minus y. This is your del x. What is y plus del y? For the point x plus del x comma y plus del y, this point is lying on the curve fx. So we can write f of x plus del x is equal to y plus del y. The corresponding value of the function y equal to fx at the point x plus del x is equal to y plus del y, and similarly for the point x comma y it will be f of x is equal to y. So we can write limit del x tends to 0. This is y plus del y minus y. What is this? F of x plus del x minus f of x by del x. Let del x is equal to h. Now, when del x tends to 0, it will be h tends to 0. So, you can write this limit h tends to 0 f of x plus h minus f of x by h. This is your value of dy by dx. This is called first principle of dy by dx. This is your first principle of dy by dx. You can write this as first principle. First principle of dy by dx. It is also called ab initio. Now, at any given point x equal to a, if you are given a particular point x equal to a, at x equal to a, we can write f dash a, or the value of dy by dx at the point x equal to a is equal to limit h tends to 0 f of a plus h minus f of a by h. For a unique tangent, it is equal to f dash a minus is equal to f dash a plus is equal to finite quantity. Hence, you can write limit h tends to 0 minus f of a plus h minus f of a by h is equal to limit h tends to 0 plus f of a plus h minus f of a by h is equal to a finite quantity. That is why we have said, what does differentiability means? Differentiability means the possibility of drawing an unique tangent of a given point of a curve. If we can draw more than one tangent at a point, it is not possible, it is undefined. So, we said when a unique tangent can be drawn to any given point of a curve, then the function is said to be differentiable at that given point. Note 1. If fx is continuous at x equal to a, then it is not necessary that fx is differentiable at x equal to a, but the converse is true. I said if f(x) is continuous at a point x equal to a, then it is not necessary that f(x) is also differentiable at that point, but the converse is true, because for such cases this is a function where at x equal to a the function has a sharp edge. At this point you cannot draw a unique tangent, because there is some possibility of drawing more than one tangent. Like this, you can draw infinite number of tangents at this point. So, when the function has a sharp edge at that point where we need to find the differentiability, you may get more than one possible tangent. That is why we can say at those points function may be continuous, but it is not differentiable. So, if f(x) is continuous at x equal to a, then it is not necessary that f(x) is differentiable, but the converse is true. Why converse is true? If you say a function is differentiable, that means a unique tangent can be drawn at that point. To draw a tangent, the point must be there. When point is there, that is the function is continuous, because if you are given these cases, now this is not a continuous figure. At x equal to a, this is discontinuous, that is the point is missing here, it is a missing point discontinuity. Now, you cannot draw a tangent at this point. So, to draw a tangent, the point must be present. So, the function is continuous. That is why we said if f(x) is continuous at x equal to a, then it is not necessary that f(x) is differentiable at x equal to a, but the converse is true. Now, second point is there. Number 2, second point, if f dash a minus is equal to p and f dash a plus is equal to q, where p and q both are finite quantities. Number A, if small p is equal to small q, that is p and q are equal, then it implies f(x) is differentiable at x equal to a, and it also implies, I have already said, when f(x) is differentiable at a point x equal to a, then f(x) must be continuous. So, it implies f(x) is continuous at x equal to a. Your second case is if small p not equal to small q, then f(x) is not differentiable at x equal to a. It also implies when f(x) is not differentiable, it automatically implies f(x) is discontinuous. f(x) is, but in such cases when p and q are finite quantity, it will be f(x) is continuous at x equal to a. So, you have to remember these two cases. Third note is, if a function is non-differentiable but continuous at a point x equal to a, then it geometrically implies a sharp edge at that point. For example, f of x is equal to mod x is non-differentiable at x equal to 0. See the graph of this function. This is the graph of mod x. At this point, your function is continuous, but it is non-differentiable because the left hand derivative and the other derivative are not equal. For example, if you take f of x is equal to minus x when x is negative and is equal to plus x when x is positive. If I find their derivative, it will be is equal to minus 1 when x is negative plus 1 when x is positive. Now, when limit h tends to 0 minus, that is the left hand derivative will be equal to minus 1 and whatever RHD it is plus 1. So, the value of the dividends at 0 minus and 0 plus are not equal. They are finite but not equal. So, it is non-differentiable but fx is continuous. So, we say if a function is non-differentiable but continuous at a point x equal to a, then it geometrically implies a sharp edge at the point. Now, it is number 4. Differentiability over an interval. If fx is said to be differentiable in a comma b, now this is an open interval, then fx must be differentiable at each and every point in a comma b. That is, for at x equal to c, for all c that belong to the interval a comma b. C is any point lying between a and b. At all x equal to c, the function fx should be differentiable. That is, f dash c must exist. Now, if fx is said to be differentiable in interval closed a comma b, then at the points a and b, that is at the boundary points, at the points a and b, right hand f dash a plus and left hand f dash b minus should exist, and fx must be differentiable at each and every point in a comma b. That is, for the point x equal to a, the r f dash a plus, and for the point x equal to b, the l f dash b minus should exist, because we have to include the point a plus and b minus. Here a minus and b plus are not present in the interval, only a plus and b minus are present. So we will check the differentiability for for a plus and b minus, and the function fx must be differentiable at each and every point in the interval a and b, that is at all points between a and b. This is your differentiability of an interval and full differentiability.